we have been talking about adding things to alkenes. You had a lot of that on the quiz just now. Let me show you some reactions you're familiar with and how they relate to other types of electrophilic additions. So this is section 7.7 in your book. Which, by the way, another quick check-in, since the book is now fully online, has anybody been using the new digital book? Any of the tools on there? What do we think so far? We like it. I am normally not a digital book person. I really like the feel of turning pages. I like the price of the free book, but I'm finding the way OpenStax has it, it's kind of easy to work through. Anybody hate the OpenStax book?
That I have is kind of similar to how I
Yeah. I think that they're going to have a solutions key posted by December, which is going to be a little late for us, obviously. But remember, the solutions key is always in the library. And it is helpful to not have the solutions key right next to you, because a lot of us will check it instantly. But anyway, we'll talk more about the online book at the end of the course, because I'd like to get some feedback. Obviously, this is the first semester I'm doing this, so I'd be curious to see, are we using it at all? Do we like it? Do you want me to go back to it? I mean, I guess you could always purchase the book if you wanted to purchase it. Anyway, in the book, which is online or not online, section 7.7 talks about other electrophilic additions to alkenes. So you've seen some where we have, and I'm going to start introducing some non-symmetric alkenes. We're used to adding things like HCl, HBr, that sort of thing, where an H is going to add to one side and the chlorine is going to add to the other side. I'll focus on just the chlorine here. It's going to add here. We talked about in the action center that nobody liked. Action center freaked you guys out. And it was meant to be hard, but it wasn't meant to be like the worst thing ever. If you had H3O plus, remember, whenever you see H3O plus, that's what's the name of this fancy name? Hydronium. H3O plus is the combination of a strong acid, something like H2SO4. That's sulfuric acid and water. If you mix a strong acid and water together, it makes H3O plus. You'll often see it written just like this, H3O plus, but this is functionally how you would do it. If I said, hey, go to the lab and add H3O plus to this, you would add sulfuric acid to water and then pour that into the alkene. What am I going to add to my alkene? What's H3O plus add to an alkene? Action centers. Water, which is going to be in the form of OH. Talk more about that one in a little bit, but that's the one that has the multiple intermediates. And I think that's what we didn't like about the action center, is that you're used to going alkene, carbocation, product. We can do that, one hop. But this one has two hops, and we don't like the second hop. It's no good. I did not give you a 2 intermediate molecule on the quiz, so don't throw anything at my face. Torso is fair game. All right, this last one you have not seen, which is if I wanted to add iodine to a molecule, I can't add iodine directly. So I have to use potassium iodide and H3PO4, that's phosphoric acid. If you're wondering why are we adding these really complicated reagents, when you add potassium iodide to phosphoric acid, you make hydroiodic acid, the acid that's happy to see you. Hi. HI is not stable enough to put into a bottle, so I couldn't just give you a bottle of hydroiodic acid. It falls apart too quickly. So what we do is we make it in place. The Latin abbreviation for that is in situ. So making it in the situation or making it in the flask. That's why we have complicated reagents up here. I can give you a bottle of HCl. It's very concentrated, it's very acidic, but it is stable enough to exist this way. I cannot give you a bottle of HI, so I have to make it by adding these 2 reagents together. But if I do, it is going to add an iodine. to that molecule. And so we can go over the reaction mechanism for each one of these, but instead of doing that, what I want to do is focus on maybe a peculiarity of each one of these reactions. So every one of these alkenes that I started with is asymmetric. One side of the alkene doesn't match the other side. All right, so let's focus on this one in particular. Is this carbon that I'm pointing at here, the carbon with a red dot, is that carbon primary, secondary, tertiary, or quaternary? Tertiary. The carbon with a red dot has 1, 2, 3 other carbons attached to it. So we would call this carbon a tertiary carbon. How about the carbon on the right? Primary, secondary, tertiary, quaternary. This one, red dot. Oh, sorry. Yeah, my cursor must be really. Yeah, that's not very helpful. Okay, red dot. I'll start using red dots more. The carbon with the red dot, primary, secondary, or tertiary? Primary. The carbon with the red dot has 1 other carbon attached, so it is primary. Well, notice that I put the chlorine on the tertiary carbon. I did not put the chlorine on the primary carbon. Interesting. Let's go down to this one. Carbon with the red dot, primary, secondary, or tertiary? Tertiary. That one. Secondary. Secondary and tertiary. I put the OH on the tertiary carbon. Again, the more substituted carbon. Odd. Down here, red dot. Secondary. Motaz. That primary, secondary, tertiary, red dot. Mutaz. I know you do, but we're going to work it out right now. How many carbons are attached to the carbon with the red dot? 1, primary, love it. It's good to see you, sir. I attached the iodine to the secondary carbon there. Right? So in each case, I added my electrophile to the more substituted carbon. That's pretty weird. That is called regiochemistry. These reactions are what we call regiospecific. By the way, I don't know if I've talked to you guys about this. When I was an undergrad, for the life of me, I could not draw this shape. Anybody else? So if you have a similar affliction, I used to do this, as I can draw squares. Anyway, all of these reactions are regiospecific. Excuse me. Voice is back. Tickle in my throat is as well. A regiospecific means that only one of 2 possible orientations occurs. So a regiospecific reaction will make a major product. It is possible to put the chlorine over here on the less substituted carbon, but that product is not favored. So in each case, we're going to add the electrophile to the more substituted carbon. And I can tell the look on all of your faces is, why? Why are we adding the electrophile to the more substituted carbon? It is, and if I don't die up here, I will tell you all about why. Section 7.8. It's about this old Russian dude named Markovnikov. Back when the Russians had a czar, and they kind of have a new czar now, Markovnikov was a Russian guy that was working on electrophilic additions to alkenes. And his rule was that the more highly substituted carbocation is formed during an electrophilic addition to an alkene. That's a lot. Let me write it all down here. Come on, boys. Nope, 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 nope. More substituted carbocation. So notice that I'm talking about carbocations here. We don't make a carbocation as a product, we make it as an intermediate. Let me show you a mechanism that can go one of two ways. Here's that first molecule I drew for you on the last page. Or in the first page of the lecture, but as a calculate structure with all the carbons and hydrogens shown. What I'm going to do is add HCl to it and make two different carbocations. So this is a mechanism you are familiar with. What attacks what? Perfect. The pi bond attacks the hydrogen. So the pi bond is going to act like a nucleophile. Pi bond attacks the hydrogen. And then what? The hydrogen chlorine bond is going to break onto the chlorine. So we're going to lose Cl minus from this, and we're going to add an H. Now, the part we haven't been focusing on is when we do that, if the alkene is not symmetric, and this alkene is not symmetric because the left-hand side has two methyl groups and the right-hand side has two hydrogens. So the molecule has to make a choice. Is the hydrogen going to go on the right, or is the hydrogen going to go on the left? Let me show you two different ways that we can form this. The hydrogen could go here, which means the CH3s would be attached to a carbon with what charge? Are you sure? Yeah, you're positive. Yeah. So the positive charge goes on that carbon. I know, so it's stupid. The positive charge goes on that carbon. So this carbon with a positive charge is primary, secondary, or tertiary? Tertiary. So I would call this a tertiary carbocation. I like all of your faces at that point are like, one, is he dying up there? And then also two, is he going to make me say positive? Because I'm not, everyone was like, not looking at you. We're not doing this joke right now. That is a tertiary carbocation. Let's add the hydrogen to the other carbon and see what we made. Now my positive charge is over here. It's trying to be a positive charge at least. Is that carbocation primary, secondary, or tertiary? That one. That one. Primary, I agree. It is on the carbon with the positive charge has one other carbon attached to it. The tertiary carbocation is more substituted. Markovnikov likes more substituted carbocations. He says da to tertiary carbocations. The primary carbocation is less substituted. Markovnikov says niet to primary, probably. Net, no, I don't know. Anybody speak Russian in here? Okay, we'll go with niet. That sounds like a thing they would say.
sounds great to me, because it's a couple, the guys are Russian and then one from, Ukrainian.
So you hear her say "nyat" to him all the time.
They speak up together, like, to each other, but he says to the dog.
Ah. Okay, good. All right, I will remember that now. So if we form a more stable carbocation, that's how the reaction is going to flow. Now notice I'm just drawing the intermediates here. Wherever the positive charge goes, that's where the chlorine is going to attack, right? So our next step here is for the chlorine to attack one of these ions. Now, I'm not going to show you that, but wherever the positive charge is, that's where the chlorine goes. So if you notice for each one of these alkene additions that I had, the first step is going to be to generate a carbocation. That sets the regiochemistry. Positive charge, counter ion attacks. It's going to be a chlorine or a water or an iodine. But wherever that positive charge goes, that's where the electrophile is going to go. And that's why Markovnikov's rule is focused on the carbocation, because if we know where the carbocation goes, we know what the final product is going to be. So a question your inner 2-year-old is asking me right now is, why? And I better not do that because my voice is going to give out on me again. Why are more substituted carbocations more stable? That's section 7.9. We're going to do this a lot today, by the way. We're going why like 7 layers deep here. Did I tell you guys that I had to explain fire to my son the other day? And I used this class. I was like, I'm so glad you asked. It's an energy difference between the wood and the combustion products of water and carbon dioxide. And he was like, what? Carbocation stability actually looks pretty similar to alkene stability. So remember what we said was, if you have an alkene that's just floating in space, it's not very stable. But the more carbons that I start to add on to it, the more stable it becomes, right? So a tetra-substituted alkene is more stable than a tri-substituted alkene is more stable than a di-substituted alkene. And then there's some isomer things in there as well. But the same thing is true for carbocations. If I go from a carbon that has just hydrogens on it to a carbon that has one other carbon on it, so carbon is going to be shown as an R group here. To a carbon with 2 other carbons attached, or a carbon with 3 other carbons attached. This is this is called a methyl carbocation. That would be a primary carbocation. Now, remember how I'm writing these things. You are hearing me say primary. You are seeing me write 1 with a degree. You are 100% not hearing me say this is a 1st degree carbon. It's not. This carbon has committed no crimes, and it certainly hasn't committed any crimes in the 1st degree. It is a primary. We just write it this way. This carbon has 2 other carbons attached to it, so it is a secondary. This carbon has 3 other carbons attached. It is a tertiary. What does a quaternary carbocation look like? Doesn't exist. Correct answer. Some of you are going to say, Dr. Green, I'm going to fall for your trick and say 4 carbons. But if you put 4 carbons around a carbon, that central carbon does not have a positive charge. So there is no quaternary carbocation. There are quaternary carbons. There are no quaternary carbocations because we can't have more than 3 bonds. Methyl carbocations are the worst. Tertiary carbocations are the best. That's a trophy. I don't know. Use your imagination. You guys are better doodlers than I am. I'll stop doodling. Get self-conscious. I really am impressed with your ability to, like, in 30 seconds, create little masterpieces. The more substituted a carbocation, I think I got one coming from Hamza. That's the look I just got, like, oh yeah, there's some art coming your way. More substituted carbocations are more stable than less substituted carbocations. So Tertiary is best, secondary is next best, primary is okay, and methyl is awful. These basically don't exist, right? They're just not stable at all. Two good reasons for why a more substituted carbocation is more stable. One is that crazy thing that we talked about called hyperconjugation. It's back. What I'm going to do is draw a little section of a molecule. That has a CH2 next to a CH3. So I'm going to draw just the interaction between these two. That would look like this. Oh, sorry, before I do this, what's the hybridization? Now that we're talking about carbocations, this is kind of strange. How many electron domains around this carbon? 3. Which means this carbon is what hybridization? sp2. So now we have this weird situation where that carbon's sp2, which means it has a p orbital. It's just empty. So the way we draw an empty p orbital is with dotted lines. There's a positive charge sitting in a p orbital. It's a place where electrons could be, but they are not there. That is next door to a what hybridization for this carbon? I almost gave it away. sp3, yep. So there's an sp3 hybrid orbital coming off of this carbon with an s orbital on that hydrogen. Now there's 2 other hydrogens coming off of this, but we won't focus on those because it gets really messy. So if these were in phase, everybody do your thing again where you look at the screen and go, squint your eyes a bunch. Now it's even harder because it's kind of ghostly over here, but you see how this lobe of this orbital and that bond kind of look like they could line up and almost make like a pi bond. It's messy. It's not a pi bond. It's trying to be a pi bond, but we can share electron density here. And let me tell you something about this carbon. It is grateful for the ability to share. It is hurting. This carbon does not have an octet. It is freaking the heck out right now. So it is looking around for other electron density to be shared with it. So anywhere it can find extra electron density is good. And what's effectively happening here is if I'm a carbon lacking an octet, it's like me running into the middle of all of you guys and being like, you guys have electron density, right? Okay, great. I'll just be near you and I'll get some of that. If I'm back here by myself, if you're just hydrogens, I have to deal with all the positive charge by myself. So me being near you all, because you're electron rich, would make me more stable. And you can share some of that electron density with me through this mechanism, which is hyperconjugation. Two things here. One, do you remember hyperconjugation from alkenes? It was confusing then, it's confusing now, probably. Two, do we understand the p orbital carbocation thing going on? It's kind of weird. We haven't talked about hybridization of ions for carbon. We talked about them for with lone pairs, but not with positive charges. So this carbon has 1, 2, 3 electron domains, which means it's sp2 hybridized, which means it has a p orbital, and that's why I'm drawing the positive charge like this. The other argument, so the more methyl groups we have around this, or the more carbons we have around this, the more hyperconjugation it can do. Right. So if these were CH3s, it could have 3 things hyperconjugating to it at the same time. The other thing that's helpful here is just induction.
The hydrogens are in the left, and they're on top of each other after the process, or?
No, just the fact that it's here at all. So this is a carbon hydrogen bond, just like this is shown. I'm just showing you the orbitals for it. So that carbon hydrogen bond is near the positive charge and just kind of sharing sideways. This is not a chemical reaction, it's just a stability thing. So if my positive charge sits in an orbital like this, when my sigma bond gets like this, they can share electron density near each other. Induction, you may recall, is just the idea that if you have an electronegativity difference between these carbons, this carbon is sp2 hybridized, these carbons are sp3 hybridized, this carbon is more electronegative than they are, and so it can just pull on the bond like a dipole moment towards itself. So if I have a positive charge and you don't, but we have a bond between us, I'm going to just pull on that bond towards myself like a tug of war and pull that electron density in our shared pair closer to myself. A tertiary carbocation can do this 3 times. A primary carbocation can do this once. So basically, if you have a positive charge, get some friends nearby to help out. All right, so let's start back where we came from, because I'm going to go another layer deep in here. So electrophiles can add to alkenes. We knew that. Now we need to deal with the fact that electrophiles add to the more substituted carbon in an alkene. So that's a new thing I have to deal with. So the question is, why do they add to more substituted positions? It's because the carbocation is more stable. Why is the carbocation more stable? This is why. So now the next question is, how the heck does the molecule even know that? Is it that, like, you don't have to draw this, but that same molecule we've been dealing with, is it that this alkene walks up to HCl and is like, okay, so what's up, HCl? I'm going to take a proton from you, and I know that if I put you over here, I'm going to make the more stable carbocation on this side. So I'm going to willingly add the hydrogen on this side so the reaction makes me more stable. Are molecules making decisions as they're going along? Probably not. There is some crazy science out there to say maybe so, but molecules, we'll assume for the time being that molecules are done, but they're just bouncing into random things. So surely some of the time the alkene is going to run into the hydrogen and it's going to just add to the less substituted carbon. Like, make the carbocation on the less substituted carbon. If you flip a coin, sometimes it should land that way. All right, so how does the Cl, or how does the hydrogen know to add at that position? This really bothered another old dude named Hammond. And he has a postulate, which is just an arrogant way of saying he thinks about stuff. All right, so Hammond's thoughts about carbocations. I'm going to write it up here, and it's super confusing, then I'll explain it and see if it's slightly less confusing. Hammond's postulate, well, yeah, let's just do it. Hammond's postulate is section 7.10. And it says that the structure of the transition state remember, we refer to that as TS, or sometimes as dagger. Resembles the closest energetic species. That is probably not very helpful. So let me just draw for you 2 different situations on reaction coordinate diagrams and see if I can confuse you even more. I bet I can. Okay, here's a tale of 2 reactions. We're going to go from a common starting material, so I'll put it on a common energy line here. And I want to make either a less stable intermediate, so high energy. Or a more stable intermediate. Lower energy. So I'll make the same things over here, put them about the same line. That's my less stable. There's my more stable. So Hammond was wondering to himself, how do intermediates form? Is it that less stable intermediates go over higher activation barriers and more stable intermediates go over lower activation barriers? Or is it kind of like life, right? You guys are a good example of this next one I'm going to draw. You are taking organic chemistry. This is not typically seen as a fun thing to do, right? You're not on the beach. There's no fun drink in your hand with an umbrella. You are taking notes, listening to whatever's going on with my voice up here, suffering. The idea behind this is that you're working your butts off so you can get to a more stable situation in life. You should have more choice when you leave NSU because of the hard work you've put in here. So you are getting to a more stable place, but you're going over a high energy barrier to get there. There are some people who are not going to work as hard as you do, but they're going to get to a less stable place. Walmart pays a pretty good hourly rate. You probably don't want to be 65 and still working at Walmart as a cashier at least, right? I don't want to hate on Walmart here. You see what I'm saying? The life kind of works this way. Typically things that are more stable require harder work. Things that are less stable typically require less work. So do molecules follow the way that life works? Or do molecules follow kind of, this would be like Occam's razor, right? It's harder to make less stable things. It's easier to make more stable things. Hammond's postulate says this is the situation. That if I have a less stable intermediate, the transition state here goes up in energy as the intermediate goes up in energy. So if my intermediate is high in energy, my transition state is going to track high with it. If my intermediate is lower energy, my transition state is going to fall with it. So more stable intermediates, in this case carbocations, lead to lower transition states. When we generate a carbocation, it's almost always uphill in energy, right? We're starting with some stable alkene. We made a carbocation, it's high up. That's an endergonic process. Have I used the dots, therefore? Yeah, okay. So this is my little shortcut because you don't want to see me write more than I need to because I know it's not awesome up here. Generating a carbocation is an endergonic process, which means it's uphill in energy. Therefore, the transition state resembles the intermediate. That's Hammond's postulate. The transition state is closer in energy to the intermediate than it is to the reactant. So as the intermediate changes, the transition state is going to change with it. I can change my starting material, but because the transition state's up here, it's going to be more closely similar to the intermediate than where I came from. So, therefore, one more. If I stabilize the intermediate, I will lower the activation barrier. This thing drops. My activation barrier for the red line is that high. My activation barrier for the blue line is that high. It takes less energy to make the more stable intermediate. So that's what the molecule is going to do because it's just the easier path. The lower the EA means the faster the reaction. So if I was really going to boil down Hammond's postulate, I would say The more stable carbocation drives the reaction forward because it's faster. The reaction can more quickly make that carbocation, so the product forms in higher yield. It's not the molecule going, let's try both and see which one works out. It's as the carbocation forms in the more stable position, it just turns into product really fast that way. There's a lot there, but that's putting a bow around the whole thing. Questions about Hammond's postulate? Let me go back through this reaction because I have 3 minutes and there's like way too much text on the screen. So can we clear this? Okay. In our HCl addition, to the alkene, we said that this bond is going to break and it's going to add a hydrogen to it. When that happens, we're going to add the hydrogen over here and make the carbocation on the more substituted carbon. That reaction is faster because the place that I'm going, the intermediate, is lower in energy. So for my reaction coordinate diagram, here's my alkene, there's my carbocation. As this becomes more stable, this line drops lower and lower. My transition state looks like my carbocation. Once that's formed, then my chlorine is going to add back to that position. And we drop down in energy. I'm trying to draw too many things at once here. This reaction, this step of the reaction sets the regiochemistry. Where the positive charge goes, the chlorine will follow. Now, the thing I want to tell you now that I've gone through the whole process here is that Markovnikov's rule is the more stable carbocation is going to drive the reaction forward. Right? But that's a lot of words. So a Markovnikov shortcut is that H adds to H. If you think about this molecule, there are no hydrogens on the left-hand side of the alkene. There are 2 hydrogens on the right-hand side. So the H added to where the H's are. And that inherently makes the more stable carbocation. When you're adding an electrophile to an alkene, add the hydrogen to the carbon that has more hydrogens. So make the hydrogens join their buddies, and you'll always make the most substituted product when you do that. Much more on alkenes, not only in this chapter, but in chapter 8. So we'll leave it there for now. If you want to practice some of this and things that we've already gone over, we have an action center in 10 minutes. Upstairs. Hamza. You do have fall break this week, but not yet. We have class on Wednesday. If I don't see you on Wednesday, I understand. My feelings will be hurt in advance, but I understand. Yeah. So okay. Ashley's going to hurt my feelings. But we do not have lab this week because we don't meet on Thursday. We'll be back on, so we'll have class Wednesday. Then we don't meet, none of your classes meet Thursday or Friday. And then we'll be back on Monday.